In this video, I'm going to explain the development of resting membrane potential, abbreviated as RMP. Uh, Resting membrane potential is a voltage across the membrane of the cell, which I'll lay that out in a moment. It's really just a separation of charge, kind of like a battery has a positive and a negative pole. Well, the cell membrane has a positive and negative pole, the inside versus the outside. And so we'll talk a little bit about how it's developed, as well as what it's for, right? How it's utilized. And so we need to start with a cell. So what we'll do is develop this membrane potential, show you what contributes to the production of this membrane potential, and along the way talk about what it's used for, right? And very basically, just like a battery is stored energy, this resting membrane potential is also stored energy. So cells utilize it to do work of some sort, whether it's literally work, moving things in or out of the cell, or in some cases it's used for cell signaling, generating a communication signal which is conveyed as a change in that voltage. Okay, so let's start at the very beginning here. We'll start with just a cell, right? I'm not going to draw the nucleus. So the black line is the cell membrane. We're going to start just with cytoplasmic proteins. And cytoplasmic proteins actually tend to have a net negative charge. So I'm going to add a little negative sign here. Now you might think, oh, okay, we just added negative charge to the inside of the cell and that makes the inside negative. Well, not really. However, because these proteins are on the inside and there are very many fewer proteins on the outside, these trapped proteins on the inside and their net negative charge tend to alter the distribution of other ions that are permeable. And I'll show you that some ions can move back and forth inside to outside. And that's actually called the Donin effect. We don't need to worry about it because it's so small, right? So the Donin effect is the effect of these trapped charged proteins affecting the distribution of other ions across the membrane here, like sodium and chloride, potassium. And it does so unequally so that it does actually generate a little bit of a voltage, okay? But no one talks about that with regard to membrane potential because it contributes so little. Okay, so let's go to the next step. So in the next picture here, we're going to make it a little bit bigger. We still have our proteins. And of course, the proteins are really important. They're just not really important to the development of this membrane potential, the voltage. So now what we're going to do is we're going to add the main membrane transporter of importance here, and that is the sodium-potassium pump. I'll put arrows on this thing because the sodium-potassium pump, right, so the pump being this blue blob I've drawn here in the membrane. So that's a membrane protein. It utilizes ATP for energy. That means it is a form of active transport. So ATP is used, right, which of course means that we break that ATP and release a DP, diphosphate, and then of course the free phosphate group, which is abbreviated PI for inorganic phosphate. Okay, so we're just breaking off one of those phosphate groups off of ATP, and we're utilizing that energy to drive this pump. All right, well, great. So now what I'm going to do is I'm going to erase that because we don't really care. I mean, we care, but we don't really need it to explain what's going on. So we're using the ATP, and what we're doing is we're moving sodium out and potassium in, right? So at the ends of these two arrows, we're moving sodium out of the cell, we're moving potassium into the cell. Now, we actually move more sodium out than potassium in. So we actually move 3 sodiums out for every 2 potassiums in. Okay, so now you might say, wow, so we're making the outside more positive, right, than we are the inside, right? In other words, we're having, in effect, right, we're having a net +1 positive charge moved out of the cell. So you might say, oh, well, that's generating the membrane potential. And again, it does contribute. This pump is called electrogenic, right? That term, electrogenic, basically means it is producing an electrical potential by moving an unequal number of ions here. But again, it's just kind of like this Donin effect that I was talking about with the proteins. It's very small. Now, that's not to minimize the importance of the sodium-potassium pump, which is enormous. Right? The sodium-potassium pump is hugely enormous in generating these gradients. In other words, there's more sodium on the outside of the cell than on the inside, and there's more potassium on the inside than on the outside, the exact opposite, right? Based upon the direction of these, that we're moving these ions. The fact that it's unequal generates a very small difference in negativity. So we could start to add negative signs on the inside of the membrane here if we wanted to. But I wouldn't get carried away with adding too many of them because it's such a small voltage generated so far. But we do have the distribution of these two main ions already, right? More sodium on the outside, more potassium on the inside. Well, now let's add like probably the critical element in generating our membrane potential. And what I'm doing now is I'm adding, this purple thing is supposed to be a potassium leak channel. Right? And so this is a protein that allows potassium to pass through the membrane. Right? The membrane itself is very impermeable, not permeable to ions because they're charged. And therefore, which means they're hydrophilic, which means they like water, not fat. Well, the membrane is fatty, right? It's a lipid bilayer. And so the ions tend to not pass through the membrane very readily at all. So we have to give them a pathway, right? So here we're using a pump, right? A different kind of protein is called a channel, where it just basically creates a pathway across the membrane. And since this one's specific for potassium, it allows potassium to do this, right? So it's allowing potassium to leak out, but then it just gets grabbed and pumped right back in, right? So this potassium's kind of going around and around, which is one of the reasons people call the sodium-potassium pump the sodium pump, right? Because it's really, moving more sodium really than potassium in combination with this leak channel. Okay, that's fine, but here's the big effect of this potassium leak. The big effect of the potassium leak is the positive ions, the potassium being moved out, is adding positive charge to the outside of the membrane, right? We're taking potassium, a cation, and putting it on the outside. Yeah, and it's being grabbed and being put back in, but remember, this thing is constantly leaking, so we're constantly adding positive ions out here. Well, as those positive ions leave the inside of the cell, what's left behind? The anions, right? And it's tending to sort of draw those anions toward the channel as well because they're attracted, right? Positives and negatives are attracted, but they can't pass through it. And so what happens? Well, guess what? They sort of line up here across the membrane, right? And there are multiple copies of these pumps and channels, so this is happening everywhere. Well, now we get a much more significant membrane potential. So 90+% of the membrane potential comes from potassium leak. Right? Potassium is the predominant ion involved in generating the membrane potential. There you go. And so you're going to end up with this. Highlight it. Right? Which is a separation of voltage, a separation of charge. Right? We could put a little knob on one end of it and make it look like a battery if you wanted to. Right? And so that is stored energy. That is a voltage. And again, at rest, that's called RMP, right? Generically, it's called the membrane voltage, or V sub M, voltage of the membrane, right? When the cell is at rest, that voltage is RMP. Anytime it's the voltage of the membrane, or VM. And it ranges from by about minus 50, this is most cells, to about minus 90, 95 millivolts. Now, the batteries you have in your house are in volts, right? 1.5 volt, 6 volt, 9 volt batteries, right? So this is a very small battery, but again, this cells are very tiny. They don't generate the enormous voltages, but it's still stored energy. Okay. Well, now all we need to do to sort of complete the picture for generating the difference between cytoplasm and extracellular fluid with the primary ions at least, and this is shown in a bar graph in a separate figure, so the difference between inside and outside between the ICF, the intracellular fluid, and the ISF, that's the interstitial fluid, right? And so to complete the picture, we have to add a few more membrane proteins that are contributing to the distribution of other ions. And so let's draw one more cell here. And we'll add everything to it. We'll make this one the biggest. Okay, so we've got our sodium-potassium pump. High sodium on the outside, high potassium on the inside. We still have our cytoplasmic proteins that tend to be anions. We've got our purple potassium leak channel. That's going to allow this potassium to leak and generate the large majority, 90+% of our membrane potential, right? Again, that would be everywhere. Okay, and now what we need to do is figure out how, like, where are the other ions and how do they get to where they end up in terms of their gradients. And so let's add, here's a key, another pump. This pump moves calcium out of the cell. And that's a divalent cation, it's a 2+ instead of 1+ like sodium or potassium. And this is also using ATP, right? That makes it a primary active transport. Definition of primary active transport is a membrane protein using ATP to move an ion or a solute, right? This guy was also primary active transport. This was a leak channel, right? This is potassium leak. Right? So we've got 3 of them now. The only other really major ion we should probably talk about is, pick a color here, is chloride. Sodium and chloride are the 2 dominant ions in the extracellular fluid, the ISF. Remember, the ISF is out here. Interstitial fluid, right, surrounding the cells. This is the cytoplasm, intracellular fluid, same thing. And now we need to talk about chloride. Well, chloride is a major ion in the ISF, in the extracellular fluid in general. But now remember, the inside of the cell generated by that potassium leak, right, all the way around here, and, right, of course, accumulating our potassium ions right on the outside of the membrane. And this is very localized, this charge separation, the voltage is very localized to the membrane. Right? It's not in the general cytoplasm or in the interstitial fluid. There's no net difference in the number of cations and anions. It's a spatial separation right here at the membrane. What's this chloride going to do? Well, first of all, chloride negative likes the outside of the cell because positive ions are out there. And does it like to, ions don't like anything, but right, would it tend to enter the cell, which is more negative? No. Right? So chloride tends to be passively distributed, but repelled from entering the cell by the cell's negativity. And so the concentration tends to be very high on the outside. So we've got 3 ions that are high on the outside, chloride, calcium, and sodium, and 1 ion the potassium that tends to be high on the inside. Now, there are other ions, and we're not mentioning here. There are other anions on the inside of the cell, like phosphate ions and things like that. But they're much lesser importance when we talk about membrane potential and changes to membrane potential. Right? The last thing to draw here is a group of it's not ion channels, sorry, but channels. Look up our new color here. That are permeable not to ions, but to water. Right? So this particular channel is essentially a leak channel. It's passively open all the time, but it's permeable to water. And what it does is it allows water to move readily in and out of the cell based upon osmotic gradients, based upon, let's say a cell takes up a bunch of nutrient molecules. Well, water would tend to enter to keep the concentration of those two solutions balanced. Let's say this cell was getting rid of a lot more of waste products. Well, it'd be moving solute out. Well, guess what? Water would tend to follow it out, and the cell would tend to shrink a little bit. And so water moves readily across this protein, which is known as an aquaporin. Right? It's a very literal term there. Aqua for water, porin for pore, and it's abbreviated as AQP. All right. Now, the last thing I'll add, so all cells in the body do this. All cells generate a membrane potential, a VM, a voltage across the membrane. They use it to do work. There is a subset of the cells of the body that change membrane potential through the expression of another kind of channel, right? And we'll have to talk about those when we talk about muscle tissues and when we talk about nervous tissue. And those channels are gated channels. So if I add another channel up here, right? And there are several types of gated channels. So I'm going to draw one specific type, and this one specific type has a receptor on it for a molecule, right? And that molecule looks a little wedge shape here to fit in that spot, right? And again, there's a variety of factors that would open different types of these gated channels. Gated meaning they have a door, and so I have to add my door here, right? And so when this molecule for this particular type binds to this channel, it's got a gate that would swing open, right? This gate would normally be closed on the inside of this, but when that guy binds, right, the door opens, and it allows some particular solute to either enter or exit the cell based upon its gradient, right? And I will have to talk about in another video those gradients and what they mean, right, and how it determine which way a solute would move. But for instance, sodium is in high concentration outside the cell, so its concentration would tend to make it enter the cell, right? In addition, it's positively charged, and the inside of the cell tends to be negatively charged, so it's electrically attracted to the inside of the cell. Guess what? If this pinkish purple cell, gated channel over here was a sodium channel, when you opened it in response to this chemical binding it, a hormone or a neurotransmitter, then sodium would enter the cell. Positive ions would come in, and it would make the membrane potential become more positive, right? Because you'd be canceling out some of these negative ions on the inside of the membrane. And that's really where we'll go when we start talking about these excitable tissues, which is really 2/3 of this course, right? To a degree, right? Because we're talking about nervous tissue, where cells are actively changing their membrane potential for a reason to communicate. And in a muscle tissue, the same thing happens, but it's used as a stimulus. That change in membrane potential is used as a stimulus to cause those cells to contract, right? And so we'll follow up with this. This is a theme that carries through, like I said, because all cells do this. All cells generate a membrane potential, and then a subset, and they use that stored energy to do work, and then a subset of them have these specialized channels where they manipulate that membrane potential for a particular purpose, for stimulating the cell, or sending electrical signals of some sort. Okay? And there you go. You've got resting membrane potential, its development, Keep in mind the key factor for the production of that membrane potential is the potassium leak, right? There is a sodium leak channel. I don't even tend to draw it because it has such low permeability. It doesn't really contribute much to membrane potential. It's really all about this highly permeable potassium leak channel, putting cations on the outside, leaving anions behind on the inside to generate this separation of charge, which we call the membrane voltage or the membrane potential.